Well, welcome everyone for this week's Western Hemisphere Virtual Symplectic Seminar. We're very happy to have James Pascaleff from UIUC talking about categories obtained from Pant's decompositions.
Okay, thank you, Catherine. Thank you for inviting me to speak virtually here. Today I'm going to talk about some recent results that I've been working on with Nicolo Sibilla. So this is about thinking about Pant's decompositions. So, by the way, I mean just the one-dimensional pair of Pants, i.e., the sphere with 3 points removed. That's the only that's the only thing I'm going to talk about today. So I want to talk about how you can glue together categories associated to the pair of pants, and what you can get, and trying to classify all the things you can get. Okay, and it turns out that the answer is, I mean, at the end of the day, the answer will not be maybe terribly surprising, but I think it's a very neat story. So that's what I'd like to talk about. Okay, so let's just recall, one place where this comes up. So I'll just, let's see, do I have my highlighter here? Yeah, so let's just look at here, or maybe I'll change it to like a different color. Let's consider, mirror symmetry for a possibly punctured Riemann surface, S of negative Euler characteristics. So this would be like a compact surface of genus greater than 2, or a punctured sphere with at least 3 punctures, etc. Well, what kind of mirror symmetry do we expect for this? Well, as many of you know, we expect the wrap Fukaya category of S to be equivalent to dB sing of X for some singular algebraic surface X. Okay, and this expectation, has a long history. I think at least going back to 2008 or 9, maybe earlier. Work of Kapustin, Katsarkov, Orlov, Yotov for mirror symmetry for general type varieties. Another work, working out that kind of story is due to Gross, Katsarkov, and Rudat. In the case of curves, there's results for genus 2 by Zeidel, Efimov for genus greater than 2, Abazaidaru, Efimov, Katsarkov, Orlov for genus 0 with punctures. And the one that's closest to the perspective that I'm going to present today is due to Heather Lee, which approaches it via taking your Riemann surface and decomposing it into pairs of Pants. So yeah, that's the one that I'm going to be following today. And of course, there's many other papers on Fukaya categories of surfaces, mirror symmetry for surfaces, other aspects. I'm not trying to survey all that literature right now. Okay, so let's focus on Lee's approach, and maybe talk a little bit more about what the precise statement is. In particular, what is this surface X that's the mirror to the surface S? Okay. So in Lee's approach, what we're doing is, one way to think about it is, you could say, let's start with some toric Calabi-Yau threefold Y. And we can look at the toric boundary divisor of that toric Calabi-Yau threefold. Now that toric boundary divisor, you often draw this thing called the moment graph. So it's a graph that describes the combinatorics of that boundary divisor. So that boundary divisor is some normal crossing surface. You might get a graph like let's say this one here. So you get some kind of graph here. This would be like the canonical bundle of P2. So here you have the moment graph for this toric Calabi-Yau threefold. Now that singular surface, well, you can take dB sing of that, right? You can take the derived category of singularities of that singular surface, which means take coherent sheaves, mod perfect complexes. Well, how does this graph reflected in the geometry of that surface? Well, you could say, well, this graph really, each edge in this graph really represents, a curve in the singular locus of X, right? So I have these P1s, these A1s sticking off. Okay. And they meet at these points, which I will call triple points. So generally speaking, my terminology for these things is I call these triple points. Okay, just where the 3 things meet. Okay. Now, another thing you can do is you can build a surface from this, and what do? Well, you say, okay, for each vertex of this graph, I take a pair of Pants, and then when there's an edge between 2 vertices, I connect those pair of Pants by gluing them on a circle. Okay, and you build a surface that way. And what's the theorem? The theorem is that the wrapped category of this surface is the dB sing of X, of the torque, of the boundary divisor of the torque Laplace threefold. And you kind of see the correspondence, geometrically, why these things are dual. And how does Lee actually, establish this? Well, she proves that, both sides here. So this dB sing thing, that's something built from, some kind of coherent sheaves on X. So it's, it's coherent sheaves. What is it? It's, co mod perf, co X, dB co X, mod perf, right? I mean, and, you can prove that that object satisfies some form of descent. In other words, when you can cover the surface X by, in fact, Zariski open subsets where on each subset it looks locally like this picture. Okay, so let's see. So let's switch from my highlighter. So locally, that singular locus looks like this, right? This XYZ equals 0 inside A3. So sort of by restricting to a Zariski open subset, you get that guy. And of course, locally, this Fukaya category quote looks like pairs of pants. So you get the wrapped Fukaya category of the pants. And then, well, say by mirror symmetry for the pair of pants, say the Abuzaidaru, Epsilon, Katsukov-Orlov result, that those are equivalent. And then, Lee has to establish that the wrapped Fukaya category also satisfies the corresponding form of descent. So she has these Lee restriction functors. Okay, I mean, I'm not going to necessarily use any of those details in this talk, so I'm just going to cite that. There's a way to, match these two sides by saying, well, they match locally and they both satisfy the same form of descent. And okay, and then you recover mirror symmetry for, the surface for S, being mirrored to X. Okay, or to the singularity category of X. Okay. So that's, that's wonderful. Okay, it's a wonderful theorem. Now, all right, so that's kind of a known thing. What do I want to talk about in this talk? See, any questions or comments so far? Let's see, I want to pause for that. All right. So what do I want to talk about today? Well, in this theorem, I think it raises a couple of interesting things you could ponder. One thing is that the mirror is extremely non-unique, because it's like, right, how many, well, these are punctured Riemann surfaces, right? So, there's two things. There's the genus and the number of punctures. Those are the two numbers that classify those surfaces. Whereas, toric Laplace threefolds, there's many combinatoric, the combinatorics you can get for this graph is, can be very complicated. So, well, so Lee's theorem says all those dB sings for all those different surfaces are equivalent. That's a consequence of her theorem. You can, of course, try to prove that directly using, birational geometry, like these Calabi-Yalls can be related by flops or other types of transformations. And you could, argue that the direct category of singularities doesn't depend on the graph, only the, genus and number of punctures that way. Okay, I mean, there's ways to do that. But I want to have, maybe a bit of a more intrinsic characterization of what exactly is it about this surface X that makes this true? What is, if I give you some normal crossing surface X, can you figure out whether it's mirrored to a Riemann surface, whether its derived category of singularities is the Fukaya category of a surface? So can you, is there just some abstract characterization of these X's? Okay. That's one question you can answer that you can ask, excuse me, that I hope to, have some kind of response to. Another thing you can ask about is, well, this gluing and descent, or what's called descent for categories, can be delicate. I mean, Lee has to use these pretty carefully constructed chain models to get the matching. You can ask, is there a sort of a more abstract or formal way to do this? Just sort of characterizing, I mean, all the different gluings here. Okay, so I want to illustrate a little bit of the difficulty in 2. So I think I'll talk about a bit first about 2. Sort of what is the difficulty in 2? Here's one difficulty that I noticed that kind of set me down the path of what I'm talking about today. Let's just go back to the concept of matrix factorization. So matrix factorizations, of course, are one way to get at DBC. Okay, so in this particular case where X, I should say, in this to connect X, the surface X is meant to be the fiber of a function, where F is a morphism from a smooth variety Y to the line. Well, what are matrix factorizations? Well, according to Orlov, what are you supposed to look at? You're supposed to look at, pairs E0, E1, which are, vector bundles on Y. And then you have morphisms D0 and D1. And this gives you sort of like a Z2 graded complex, except it's not a complex. The square of the differential is F times the identity. So F is the defining function there, is your potential. Okay, sounds good. So you can consider that. Now, here's a very dumb question, seemingly dumb question. What happens if you rescale the potential? So for example, what happens if I take F and I just rescale it by a constant, like a scalar, something in the ground field? Well, you would say, well, that really shouldn't do anything interesting. Well, because why? Because you can say, well, look, what does that do? That's sort of what's the effect of that? Well, you kind of are like inserting the C here, right? You change the definition slightly, you sort of insert the C here. Well, I need to have a C on the other side to compensate. Well, I can do that. I could just rescale D1 by C on all of the matrix factorizations, okay? Or I could rescale D0. Or if C has a square root in the field, I could multiply both by the square root of C. That's kind of the most symmetric thing you can do. Okay, that gives a bijection on objects. So that's actually a bijection on the objects. Here's kind of a funny question. Does it extend to a DG functor on these matrix factorization category? So what does that mean? So, the point is, well, I want to be clear, the HOM, I'm considering sort of just these sort of two-term, these kind of like Z2 graded complexes, right? Where it's not a complex, it's a curved complex. But, if you consider just that and you say the HOM space is like, okay, the odd, the even part is, maps between, it's degree 0 maps, the odd part is odd maps, and you want to have a DG functor on that object. It turns, this is very strange to me, but I believe the answer to this is just no. It just does not extend to a DG functor. You can't, when you rescale the potential, you can't make it a DG functor in this sense. What happens if you're wondering what exactly happens, you can kind of do some kind of clever rescaling, and it ends up rescaling, basically it rescales if you think in terms of A infinity operations, this is like the operation that rescales the D A infinity operation by C to the 2 minus D. So it's sort of mu D goes to kind of like C to the 2 minus D mu D. It's this kind of scaling that ends up going on. And you can't necessarily trivialize this. Well, okay, so still not that different. And of course, it can't be that different because the classical homotopy category, the homotopy category as a classical triangulated category doesn't change when you rescale the potential, right? How do I say? The homotopy category of this MF, it's just DBCing all the time. It doesn't actually depend on rescaling the potential. So I think what's going on here is that in this Z2 graded setting, this is some kind of small or, possibly, you might even say trivial, counterexample to a version of the Lintz-Orlov uniqueness of a DG enhancement. It's just saying, you can rescale this potential and you can get, it's not necessarily true that if you have a triangulated category of this kind, there's a unique Z2 graded category, DG category, whose homotopy category is this DBC. Okay, so that's a little bit strange. But then you can say, well, it doesn't really change things that much. Okay, well, we'll see actually that this kind of rescaling thing has actually a pretty significant effect when you start gluing. Okay, maybe I'll get to that. Let's see. Any other questions about this? I know this. Okay. Comments. You can also comments if people have comments about this.
Can I ask one, please?
Yes, please.
So the question was, the identity functor is not a DJ functor, but is it not possible that you can find some other kind of functors?
Well, I think yeah, the identity functor is not, well, I mean, it's not really the identity functor, it's this rescaling functor.
Okay, yeah.
Yeah, I mean, I tried hard and I couldn't do it. And then I'll explain how to get the equivalence. Like, they are actually equivalent in a different sense. That's the thing. Like I think the failure of this being equivalent is like an artifact of setting up the problem in the wrong way. Okay. Yeah, I mean, yeah, you're right. Yeah, I tried hard. There's no, yeah, it's hard. You see, the thing is, this is so simple. You try that, you have to write down some universal formula, and you just can't. So that's why throughout this talk, what I'm actually going to do is I'm not going to work with Z2 graded categories, but I'm going to work with what are called two periodic categories. So what does that mean? What is a two periodic category? What it means is that it's a category which is actually Z graded. I mean, the grading is by the integers, but and it has a translation functor, a shift functor, but it's linear over. But okay, but the point is that the double shift is isomorphic to the identity. So in other words, you have a natural isomorphism from the identity functor to the identity functor shifted by 2. Okay. But you have to actually choose this isomorphism. This isomorphism is now part of the data that you have to kind of carry around with you everywhere. Another way of saying that is that this category is linear over this ring. Well, this is actually a graded ring. So it's the Laurent polynomials in a variable u, where u has degree 2. So in other words, sort of this u is like, yeah, okay. And then the kind of solution to the previous kind of conundrum was that, well, if you rescale the potential by f, you actually rescale this u operator by the inverse. That's all that's happening. Basically, changing f rescales the two periodic structure. And that's the point. The point is that this kind of that means that so the point is that this rescaling of the potential can be kind of absorbed into a DG equivalence, but you have to be able to rescale, you know, how to say, you have a morphism x and then you have u times x. And the point is that you rescale x and u times x differently in this equivalence. Yeah, so rescale, so that's the kind of upshot here. So actually they are equivalent as two periodic. So like if you rescale the potential, you get two different two periodic DG categories, and they are equivalent as two periodic DG categories. It's just that the U operators on the two sides don't quite correspond. They do correspond up to rescale. Okay. And so yeah, so actually what happens here is that it shows you that this dB sing x, which is, you know, mf of yf, admits, you know, many two periodic structures. Okay. And so in fact that's creates some of the freedom in what I'm going to talk about, you know, now. Okay. All right. See, more questions. All right. So here's sort of, I want to set up sort of the general problem. What am I going to try to do here? Okay. So what am I going to try to do? I'm going to try to study, I'm going to say, okay, let's consider, you know, these two categories. So, you know, these are kind of the local categories in that pants gluing picture. So one category is this V. I'll call it V for vertex. It's sort of the category that lives at the vertex of the graph. Well, it's MF of A3 with XYZ, the mirror of the pair of pants, or you could say it's the Fukaya category of the pair of pants. Okay. And then there's this category associated to the edge, which is the Fukaya category of the cylinder. But I really want it to be this kind of two periodic version. So in algebraic geometry, that would be written this way. I call it, okay, sometimes this notation is perf superscript parenthesis 2 of GM, or it's perf of GM tensored with K over KU inverse. That's actually an equivalent way of doing it. This is the thing you get by taking the perf of GM, which is Z graded, collapsing the Z grading to a Z mod 2 grading, but then regarding that as a 2 periodic DG category in the previous sense. Okay. So then what do I want to do? Then I want to say, okay, what's the other input I need? I need a graph. I need a trivalent graph. Okay. So let G be a trivalent graph. Like it could be this one. It could be, that's the thing for the genus 2 curve. Okay. It could be something. Now, here's the question. What are all the different ways to glue copies of V and E over G? In other words, I want to take, what I would call the homotopy limit of a G-shaped diagram. So, basically you draw some kind of diagram of, where at each vertex you have a copy of V. At each, so there's 3 copies of V here for these 3 vertices. At each edge you have a copy of E, and then you have some restriction functor from V to E. Okay. And you want to look at that and you want to say, okay, what are all the, okay, but I'm not saying I take a specific functor. I want to consider all the possibilities. Okay. All right. So I do want, now I could, I guess if I really considered all possible functors, I would get, tons of different things. Okay. Like I could consider the 0 functor or something. I mean, okay, that's not what I want to do. I want to consider that these restriction functors, so that's like the functor from V to E, I want to assume that those functors are geometrically, quote, geometrically reasonable, meaning that they look at least roughly like what you would expect to get from geometry. So, the basic kind of local model here would be, for example, in this MFXYZ case, let me see, maybe I'll write it here. Sorry, I didn't leave myself enough space right here. Maybe I'll just write it up here. You take MF A3 XYZ. Sort of the thing you can do locally is you can sort of restrict to, I'm doing this on the B side for some reason. So, you can restrict to this thing. And then there's a Knurrer periodicity. So the point is, once you say delete x equals 0, this function here is really you could think of it as a quadratic form on the normal button. Like it's a quadratic form in the YZ variables, depending on x. And then when you use Knurrer periodicity, you get actually this perf2 of, well, sort of the x line. Okay. So I want something that looks like that, or something that looks, you could say, okay, that's sort of the B model description. In the A model description, it's like the restriction functor from the pair of pants to the cylinder. I mean, something that looks at least vaguely like that. Okay. Really what I mean is that, yeah, locally, I guess technically what I really mean when I say it's geometrically reasonable, I mean that if you look just at this piece of the diagram, just one single functor, that piece of the diagram is isomorphic to the restriction functor from the pants to the cylinder in some, local, in some reference pants. Okay, that's what I mean. Okay, so I want to study all of those different things. Okay, and I'm then going to take, the homotopy limit of this. So I'm saying, given the graph G, given some collection of functors like this, I form this G-shaped diagram and then take the homotopy limit of that. I get some category, and I want to ask, what kind of things can you get? Okay. So, I mean, according, sometimes one thing you can get is the, Fukaya category of a surface, okay, or a singularity category of certain, or of this toric Claviau boundary. Those are some things you can get. Can you get anything else? Well, what you got to think about is that. Okay, so the answer, by sort of general shape of this diagram, what you really need to understand are the auto equivalences of E. So the point is, the way this problem sets up is that what you can do is that if you had one diagram, you can look at an edge in the graph and you can change the diagram by an autoequivalence. You can twist the diagram by an autoequivalence of this edge category, E. Okay. So E is this perf 2GM, or it's the Fukaya category of a cylinder, thought of as a two periodic DG category. And now, if you want to, so what you really need to look at is the autoequivalence of that category. Say, well, how given this diagram, how can I twist it? What are all the possible twists? Now, that's one thing. Okay. Another question you can ask is, you have to see how this thing, I noticed that there was this kind of two periodic structure that's kind of important. So what you need to ask is, what happens to the two periodic structures on the pieces? What becomes of them? And does it glue up to a two periodic structure on the category C? Well, what we'll find is that depending on how you do it, it may or may not give rise to a two periodic structure on the limit category C. Okay, so that's what I'm asking. I'm pointing to this thing here. So it sort of depends. You could have a diagram where all of the functors are two periodic, and then you would get a two periodic structure on the category, or you could have one where they're not two periodic, and then you get something else. Okay, and actually, it turns out all of those things are geometrically interesting. Okay, so that's kind of the new thing. And in fact, when you have the two periodic, what I'll be saying is that you just recover Lee's result. When you assume that everything's two periodic, you're just recovering what Lee got. When you have things that are not two periodic, well, yeah, there's some twist that you can do that gives something that's not two periodic. Okay. So I'm going to proceed to try to describe sort of the answer to that question now. Are there questions about the setup? Let's see.
Hi, James. Yeah, can I ask you to clarify again, like what precise functors you're allowing? You're just saying they have to look like restriction functors. I'm a little confused about.
I mean that it's isomorphic. If you look at this, if you look at one edge, look at a single edge in isolation. I want that to be isomorphic. I want that diagram to be isomorphic to the restriction diagram of pants restricting the cylinder.
Via some isomorphism from V to pants. And
there's some isomorphism. Exactly. Okay. So yeah, you're forcing me to be more precise. Yeah, that's right. I mean, what I'm trying to say, yeah, this is helpful. So I want to say V. Yeah, I want to have this. All right. So this is wrapped of pants. This is wrapped of cylinder, and this is this thing. And I want that if you look at one edge in isolation, you get an isomorphism like this. That's right. Yeah. But then, of course, the point is that if you look at multiple edges, it's not all compatible. Okay, that's why you can twist. Okay. So it turns out you can describe this, at least pi 0 of the autoequivalences of E. So what is E? It's this Fukaya category of the cylinder. I mean, I'm needing to think of it as this kind of two periodic thing. So I'm writing it in terms of algebra because it's sort of clearer, exactly what the thing is. But anyway, this E, it's perf 2 of GM. So it's actually, you could write it as perf of this algebra. So it's actually a Laurent polynomial ring in two variables. So X is like sort of the geometric variable, and then U is this two periodic structure. Okay. And the point is, very importantly, the degree of U is 2. Oops. Deg U is 2. Just keep that in mind. Okay, so what can you do if you want an automorphism of this? It turns out that the automorphism group of this, the autoequivalence group of this category is not too big. So you can do automorphisms, so graded automorphisms of this graded ring. Or you can shift. Of course, every category is going to have a shift functor. In this case, it is two periodic, so the double shift is isomorphic to the identity. So the shift really only generates a Z mod 2 once you look at pi 0. Okay. Then we take, so basically it's automorphisms of the algebra times the shift. What are automorphisms of the algebra? Well, this is a polynomial algebra. So basically the automorphisms, what can you do? You can rescale the coordinates or rescale the variables, or you can permute the monomials. I mean, the monomials are actually sort of a canonical basis of this algebra. So they have to be permuted by any automorphism. But they also have to have their degree preserved. So what that means is that actually, forces this. So that means U has to go to, actually this is all you can do. Actually, it's easier. I wrote it as a matrix, but it's easier to just look at this bit here. I mean, this is the formula, sorry. So you just look at the formula here. So it's like, that's what you can do. You can rescale the variables, or you can, so this epsilon, you can invert x, you can send x to x inverse, and then you can send u to x to the n times u. That's what you can do. Okay, so those are the automorphisms actually that I'm going to consider. So actually those are the automorphisms I'm going to focus on for the rest of the talk. This is really sort of the new interesting bit here that you have, in particular this number n. I was wondering, like, what the heck is this number n doing? Where does it come in? Okay, so the point is that if n is 0, I mean, if you look at this transformation here, just focus on this formula. That's kind of has the information. If n is 0, then this transformation is preserving u. U goes to u. That means that this is not merely an automorphism of the category, an autoequivalence of the category, but it's a two-periodic autoequivalence. It preserves the two-periodic structure. Now, the subgroup that preserves the two-periodic structure is actually much smaller. So all you can do is rescale x and send x to x inverse. So there's a much smaller autoequivalence group if you require them to be two-periodic. Okay, but I'm not actually requiring that right now. Okay. So of course, there is some version of this diagram that does produce the Fukaya category of S. That's Lee's result. Okay. So let's regard that diagram as kind of the reference point. It turns out if you actually work out what I have in fact worked out what that diagram is in this algebraic language, and it's a little bit tricky to write down exactly how it works. But let's just say that's kind of the reference diagram. We know there's some version of these functors that gives you the Fukaya category of a surface. The natural twists that you want to do are living in this group. So what is this? So k star squared, that's rescaling the kind of the u and x coordinates. There's this 1n, 1. I don't really want to send x to x. I don't really want to flip x to x inverse because somehow the singular locus is like a P1 rather than an A1 with doubled origin. I mean, I don't know if that makes sense to anyone, but like, there's a reason why you don't twist by sending x to x inverse, because that would replace a P1 by an A1 with doubled origin. It's kind of, I don't want to consider that. And then you can also twist by this shift. So this is the shift. The Z mod 2Z is the shift. Okay. So you can do that. So, in fact, now you ask, okay, well, what structure do you get then? Well, actually, it's not so crazy to see what you get. But what can I do? Well, I can put a different twist at every edge of the graph. So, if we go back to this diagram, what I'm saying is that, relative to the reference diagram where the result was the Fukaya category of a surface, I can put a twist at every edge, right? And I can put different ones. I can choose them independently. Okay. Cool. Now, what do you get? So you could get a two-periodic category at the end. That would be if all of your twists were two-periodic. So they don't send u to x to the n times u. They just send u to u. Okay. No, that would give you something two-periodic. Okay. But if these n's are not 0, so if this n appearing in the twist, I'm going to spend a lot of time talking about n. So by n, I mean, the entry appearing in this matrix, which is also the n appearing in this formula. I'm going to spend a lot of time on that. If n is not 0, you don't get something two-periodic, but you get something which I would call twisted two periodic. So in fact, what you get is that this category, the limit category C, is going to come equipped with an autoequivalence, which I'll call phi, and there's going to be a natural isomorphism from identity to phi inverse shifted by 2. So I call this a phi twisted two periodic structure. Another way of saying it is that the autoequivalence phi is isomorphic to the shift by 2. That's another way of thinking about it, but it's not two periodic when phi is non-trivial. Okay, so that's kind of an interesting structure you can get. All right, let's see here. So, okay, so basically, okay, by the way, I just say I'm going to focus on this twist by n. You can also do this twist where you rescale the coordinates of the x and u. So that's like rescaling the kind of the gluing, the way these two A1s are glued together to a P1. You can also rescale the two periodic structures on the local pieces. That's kind of subtle to work out exactly, you know, what the, of course, not all of those parameters are effective because some of them can be absorbed by equivalences of diagrams. That's actually a bit subtle to work out exactly how it works. But if you want a pointer, those parameters, well, they correspond to things like rescaling the two periodic structure or rescaling the twisted two periodic structure. And in symplectic geometry, they correspond to rescaling the area of the Riemann surface. So there is a way to work out sort of what those parameters do. It's kind of subtle. It doesn't actually, the effect is kind of also hard to detect what the ultimate effect on the category is. So I'm just going to kind of suppress those parameters today. You could just set them to be 1 if you like. Okay, so let's talk about realizing these twisted categories in the A and B models, because that's what I want to do. That should be interesting. Okay, so here's the B model realization, and I want to say that what I'm about to present on this page is rigorous mathematics, like Nicolo and I have proved what's asserted here. So let X be a normal. So the kind of X I want to consider is this. I want to consider X be a normal crossing surface. So that means that its singular locus is curves meeting at triple points, locally modeled on, well, okay, formally locally modeled on the XYZ equals 0. Okay. And I want to assume it has, well, there's one condition you have to put, which is called graph-like singular locus. That's our term, but I don't know. There might be already a known term for it. But what it means is that the singular locus is a union of P1s and A1s. So there's no higher genus curves in the singular locus. They meet at triple points. So the triple points are, where 3 components meet. And there's 2 triple points on each P1 and 1 triple point on each A1. I mean, in principle, you could have, in a normal crossing surface, there could be more than 2 on each P1, but I don't want that. Okay, so let's take graph like singular locus. And then there's another condition, which is kind of weird, but I want to assume that, so if you take this normal crossing surface, it has this kind of dual intersection complex, which, is like, it's sort of like, you just draw, I mean, basically, in this case, how to say, right? Right, I mean, the dual intersection complex of say this guy, it really is just that, well, for the toric calabi-Yau, the dual intersection complex is just R2. It's homeomorphic to R2. For the toric calabi-Yau boundary, if I took something like the toric boundary of P3, the dual intersection complex is homeomorphic to S2. That's the thing I'm talking about when I talk about this. And I want to assume that that is orientable. Okay. All right, so those are my hypotheses. And then you let G, the graph is the graph for the singular locus of X. So there's a vertex for each triple point and an edge for each component of the singular locus. And then dB sing of that surface satisfying these conditions is the homotopy limit of a G-shaped diagram of these categories. Okay, so that's true. It is computed by some homotopy limit of this form. And you can ask, well, what happens with these twists when you twist by this n? So well, the question is, how do you determine the twist? Okay, how do you determine the twist? And the twist is determined by the topology of X, in fact. It's determined by this quantity. This looks a little bit weird. So you take the cotangent complex of X, and you take its degree -1 cohomology. So it turns out that these hypersurface singularities have, on the singular locus, you have degree 1 negative cohomology in the cotangent complex. It's actually rank 1. It actually defines a line bundle over the singular locus, and you take the degree of that line bundle on the P1 contained in the singular locus. Okay. And then that line bundle comes into play. So that determines, what is the value of n. N is the degree of this line bundle. So in the Torr-Calabi-Yau case, these n's are all equal to 0. Okay. All right, and then there's a line bundle. So the autoequivalence here is the tensoring by the line bundle, basically tensoring by this line bundle that I just described. Tensoring with that line bundle, or actually it's the dual line bundle, is the autoequivalence of dB-Sing. And the way this thing works is you get a L-twisted 2-periodic structure. So tensoring by L is isomorphic to the double shift. Okay, right, so if all NE are 0, you recover the Fukaya category of S. If the dual intersection complex is not orientable, you can twist the whole construction by the first Stiefel-Whitney class of that complex. That involves putting some extra shifts on the gluing. And there's actually a paper that came out shortly, it came out in 2021 by Ed Siegel, where he talks about that kind of thing. Gluing, it's actually that's a similar problem to what's being discussed here, but in a Z-graded setting. Okay. All right. So let's do some symplectic geometry. Okay, are there more questions about? I need to pause for questions about this bit here. I do want to talk about some symplectic geometry too. No questions? All right, let's talk about the symplectic geometry, which is maybe more interesting to you all anyway. Okay, so what I'm going to talk about here, I have to emphasize, is conjectural. Well, I'm talking about dB-Sing, and I'm doing, interesting things with dB-Sing, so it's no surprise that I'm going to want to use the theory of Rabinowitz-Fukaya categories. So, I mean, I need to credit, Ganatra, Gao, and Venkatesh for, setting this theory up. I personally, me and Nicolo, are not going to contribute anything to the foundations of this theory. Sorry. We thank, Ganatra, Gao, and Venkatesh for doing this, for setting this up. I mean, I'm just going to talk about some, and so, that's why I'm formulating this as conjectures. I actually am not, I don't really know the full construction of this Rabinowitz-Fukaya category. I'm just going to, go off of, some talks of Shield that I've seen, and see where we can go with this. But it does seem to give a coherent picture here. Okay, so one thing that helps kind of figure out what's going on to do the A model realization. So the question is, what is the A model realization of these kind of twisted gluings, right? Like where these NEs are not 0. Okay, the untwisted one, I just get the Fukaya category of a surface. But what about the twisted one? Okay, so first you have to understand the untwisted case a little bit better. Okay, so here's something that here's kind of a conjecture that's actually pretty general. I wouldn't be surprised if other people have already figured this out. So if you're in the audience and you've already figured out this kind of picture, you're welcome to speak up. But it's something about a general type symplectic manifold. So let's say Z is a general type symplectic manifold. So I'm thinking, of these higher genus curves really is what I want to apply this to. But I think what I'm about to say, at least the conjecture makes sense more generally. So let Z be a general type variety regarded as a symplectic manifold. And let KZ be the total space of the canonical bundle of Z. Okay. Well, okay, why am I passing to this? Well, one interesting thing about that is that that total space has a canonical complex volume form. I mean, right? The point is the general type thing, C1 is not 0, so it doesn't have a complex volume form, but this KZ does. Okay, so it's a tautological construction where the the canonical bundle of the canonical bundle is trivial. And it also has it is a line bundle, total space of a line bundle over the variety Z, so it has a S1 action, okay, which rotates the fibers. What I actually want us to do is take the punctured version of this. So I take KZ minus the 0 section. I'll call that PZ. I call it the principal canonical bundle. It's like the principal C star bundle for the canonical bundle. And then here I'll introduce this. Well, I mean, at least I think I'm doing this right. There's this thing called the Rabinowitz-Fukaya category of this kind of object, okay? And this thing is, I want to emphasize here that I'm restricting to gradable Lagrangians. So somehow the grading here is something I want to pay attention to. Not, I mean, I guess maybe that's what you would always do, but that's what I want to consider. Okay, so this is, again, this kind of thing where you're kind of, I mean, I must say I'm not an expert on these things. I just have a vague sense of how they work. But, it's like, the point is, you're wrapping at kind of both ends, right? Like the point is the fiber is a C star and you're like wrapping at both ends. Of course, it's it's a Liouville cobordism. It's not a Liouville manifold, this P of Z. Okay, and well, here's the thing. Another thing that I guess you could notice is that there's this S1 action, and this S1 action gives you an interesting operator on this Rabinowitz-Fukaya category. In general, when you have a Hamiltonian S1 action, you get this action of the Laurent polynomial algebra, which you think of as chains on the base loop space of S1. One kind of strange thing perhaps here is that the degree of the generator is 2. That has to do with thinking about the way that this holomorphic volume form behaves on the fibers of the canonical bundle, right? It's kind of, if you look at the fiber, the volume form is kind of like dz on C rather than dz over Z. So the sort of generating loop of the S1 has degree 2. Okay, so then that at least, so you can think of that. So here's this idea, which I was a little bit surprised by. You could think of that as giving you a 2-periodic structure on the Rabinowitz-Fukaya category. I mean, the point is that this Hamiltonian S1 action on the total space of the canonical bundle is giving you a 2-periodic structure on this Rabinowitz-Fukaya category. Conjecturally, I mean, this is all conjecture. So the conjecture is that there is a, so then if you see that, why not make this conjecture? So you could conjecture that there's a KUU inverse linear equivalence between this Rabinowitz-Fukaya category of the punctured canonical bundle of Z with the actual Fukaya category of Z itself, where the Fukaya category of Z itself is 2-periodic just because, well, it was a Z2 graded category to begin with, whereas this one is 2-periodic because of this S1 action. So the reason why I want to do this, if this works, I say this is a conjecture, if this works, it kind of geometrizes this U action. That's the point. It makes the U action something geometric that you can, actually look at. Okay, I mean, I did have, I think there's a pretty, I think if you formulate this, you'll see that there's a kind of a reasonable proof idea. Not that again, I'm trying to make this rigorous, but basically the idea is you take Lagrangians, what you do is, okay, you have to get a little bit more precise, like you take, you have to think about what is the symplectic form on this canonical bundle. So the easiest way to construct is choose like a balancing form on Z. So that's like a form on the principal S1 bundle whose derivative is the pullback of the symplectic form. And use that to construct the symplectic structure on P of Z. And then if you look at a balanced Lagrangian in Z, you can lift it. You can lift it to a Lagrangian in the total space. And in fact, balancing is important. If you take an arbitrary Lagrangian in Z, it's not clear how to lift it. But balanced ones can be lifted. And then if you I just look at, if basically what you could say is that when you look at an intersection point downstairs in Z, and you look at what happens when you lift it, well, when you lift it, you kind of get 2 Lagrangians upstairs that intersect in a basically in something like a ray. And when you do this Rabinowitz wrapping, it looks like you produce this KUU inverse. So the contribution of an intersection point downstairs is a copy of KUU inverse when you do the Rabinowitz type wrapping. And I'm treating that like in a very naive way. Like I think there's a lot to do if you wanted to make this rigorous, but just naively, there seems to be an idea for how this works. Okay, so I wanted to do that because that gives me extra room to do my kind of twisting. Okay, by the way, this relates to a recent conjecture of Lakili and Ueda, which is based on a previous conjecture, I believe, of Denis Yaru. But here it is, their conjecture. This is their conjecture, not mine. It says, take a compact Calabi-Yau of any dimension, why not? Let Z be an ample divisor and look at the complement. Then the wrapped Fukaya category of U modulo the compact Fukaya category of U is equivalent to the Fukaya category of the divisor, Z. So if you kind of believe, if the story I just said is at all right, that seems to, there is kind of an approach to this conjecture via that, which is, well, you have a divisor in a Calabi-Yau, so you use the adjunction formula. The normal bundle of that divisor is isomorphic to its canonical bundle. And then, okay, I would argue that the wrapped Fukaya category of U modulo the wrapped Fukaya category of U is going to be this Rabinowitz Fukaya category associated to the punctured normal bundle of the divisor that you removed. But that punctured normal bundle is the punctured canonical bundle. So I cite Ganachar Galvekdesh. I think, some statement like this, I know that there's subtleties that I'm probably, messing up here, but, this seems to be one of the general expectations for how these things work. So then wrap mod compact of U is the Rabinowitz Fukaya of this thing I just talked about. And then if the previous conjecture is true, that would be the Fukaya category of Z. So it kind of relates to known stories. That's why I'm saying, yeah, okay. Let's see, are there questions or comments about, this is kind of maybe shifted gears a little bit, but,
I'll have a question, but maybe later.
Okay, we can talk about it later. Okay, yes. All right. So let's go back to the curve case, since that's what I actually, wanted to talk about. So what are you going to do? Well, so what you're going to do is you're going to twist the gluing somehow, right? Like I want to go back. Let's just recall, I had this kind of digression about some stuff, right? I want to figure out what is this n doing, these n's, right? So this n had to do something with some kind of degree. I want to figure out what that's doing. So how do I twist the Fukaya category of a surface? Well, my strategy for that is this. Let's use this conjecture. Let's put Z to be S. So S is the surface. So I don't really know how to twist the construction of S. There's a classification of surfaces. I can't really do anything. But I could move over here. So instead of twisting the construction of S, I would twist the construction of P of Z. So I take this principal canonical bundle, which is like you call it also the principal frame bundle of the surface, right? Because the canonical bundle is just the cotangent bundle. Okay, so you can take the principal cotangent bundle of the surface, yeah, so I'm going to twist that structure. Okay, so and it turns out that there's a way to twist that. And then that matches. I mean, that's the story I'm gonna say here. So what you need to realize is this. So suppose I have some kind of cylinder here that I want to twist along. Hold on, where is this thing? So this is so there's some cylinder I want to do a twist along the cylinder. So there's kind of also this core circle here. Let's call that circle, I don't know, C. Well, I call it C. I don't know. Let's call it L or something. Okay, there's that kind of core circle. So let's suppose what I'm really imagining is this is sort of, I have a Pants decomposition of the surface. I'm looking, this L is one of the circles in that Pants decomposition, and I'm just doing something locally near that circle. Okay, so near that circle, this P of C, so C is the cylinder, okay. The principal canonical bundle can be trivialized. I mean, the tangent bundle of a cylinder is trivial. And actually it has so you get so this principal canonical bundle is C cross C star. And this thing, it emits an obvious like torus vibration. So I'm kind of using a little bit of SYZ, philosophy here. So there's a torus vibration on this thing. And the base is like a strip. Okay, so like the vertical direction in this picture is like the C star. The horizontal direction is like the cylinder. Also, an interesting point is that because I'm using the principal frame bundle of a Riemann surface, there's actually canonical affine coordinates on this because, so there's sort of a canonical basis for H1 of these tori. So what is the torus? The torus is like the loop in the fiber across the loop in the base, right? I have these tori here in the base, and then I have the loops in the fiber. Those are the tori in the torus vibration. Those tori actually have a canonical framing because you can take the loop in the fiber. That's one kind of canonical loop. But you can also take the loop on the base and take its cotangent lift. So that's another canonical basis element. So you do get a canonical framing for this tori, and hence you get canonical, up to maybe sines or something, you do get canonical affine coordinates on this little bit of a torus vibration over this edge. And then what can I do? Well, I can re-glue that using an element of SL2Z, right? That's what I'm going to do. I'm going to say, well, okay, I kind of take this strip, I kind of cut it, and then re-glue the two pieces using an element of SL2Z. And then I ask, well, okay, well now wait, I have all elements of SL2Z that I could use. Well, what's the requirement? I actually want the resulting manifold to still have C1 equals 0. I want it to still have I want the gluing to preserve the complex volume form. And that forces the gluing to be of this form, to be of the form that I want. So actually that's how it matches. The gluings that you're allowed to do here are upper triangular matrices because you want to preserve the grading form, the complex volume form. So it turns out that that's exactly the opposite. Those twists, they don't preserve the fibers of the C star bundle. See, one thing you can do with the C star bundle is you can twist the gluing and get another C star bundle, right? That's not what I'm doing. I'm doing exactly the opposite. So these are the twists that don't preserve the fibers of the C star bundle. They preserve actually the sections in this, they actually preserve the sections in this local picture. And an alternative description of what this gluing is doing is you can do this kind of shearing. Another way to describe it is what you're doing is you're sort of cutting the manifold, and then you're gluing in a copy of the symplectic mapping torus of a Dane twist. And actually, okay, I didn't quite, okay, so let's just say it's an n-fold Dane twist. Okay, with some convention for what the positive Dane twist is. It's an n-fold Dane twist, where n is the shear that you do here. Okay, n is the shear that you do in this matrix. That's another way to think about what you're doing to this manifold. Okay, so you can denote the result by this P of NE. So in other words, I do this kind of shearing. I have a Pants decomposition. I do this kind of shearing one at each edge for any some different numbers Z. This P of NE is then going to have, I claim, a symplectic automorphism given by the n-fold Dane twist along the, it's kind of locally given by this sort of n-fold Dane twist, lifted to the re-glued manifold. And the conjecture is that, well, the Rabinowitz-Fukaya category of this thing exists. I actually have questions about whether that's even reasonable, but okay, let's just say it exists. And there is a natural isomorphism from the identity to this monodramy mu shifted by 2, or I wrote it as mu inverse, but okay. And that's sort of the first part of the conjecture, that this actually makes sense. And also that the structure just described is obtained from the twisted gluing. In other words, it does actually match the mirror story here, where you had it does actually match this gluing, okay, where you had the normal crossing surface. Okay. Yeah, there you go. So you can do different things with this. So yeah, you have these things. One thing that's connects, it still connects back to Fukaya categories of surfaces via the work of Maxime Jeffs, because what do I have? I have now this Rabinowitz-Fukaya category, conjecturally, which is mu twisted 2 periodic. So mu is isomorphic to a shift by 2. I could do then a further localization that makes mu isomorphic to the identity. And if you make mu isomorphic to the identity, you also make the shift by 2 isomorphic to the identity. So you get a 2 periodic category. So that's this kind of, that's, that's what Maxime Jeffs studied. So I guess I'll say it as a conjecture that, you can construct another natural transformation from the identity to mu, and localizing with respect to that, you're going to produce the Fukaya category of a nodal curve, a nodal Riemann surface. That does match on the B side. We can do that rigorously. So actually, there is some kind of sign issue there. You need these twists NE to be positive or non-negative. If they're non-negative, then you can do this. You can do a further localization that produces, so I guess the thing you want, what's called relative dB-sing. So this is, it's a localization of dB-sing. Maybe I won't try to explain that right now. Kind of involves a bunch of definitions. By the way, here's an example. If you wanted a picture, maybe I'll just end here. What is going on here, with these twists? Okay, maybe Catherine, can I have just like 2 minutes or?
Sure, go ahead.
Okay. Yeah, so let's take a classic example, the quartic surface in P3. So let Z be the intersection of the quartic with the toric boundary of P3. So you get this picture. This blue thing is like the tropical picture of the curve, the boundary divisor. So so it's 4 genus 3 curves, 4 genus 3 curves meeting at 24 nodes. Okay, so the mirror of the complement of Z is the toric boundary in this Crepin resolution of P3 modulo, the group. And what you'll actually find is that, maybe I should. It turns out that, you get something that really is twisted. So, I'm saying that, you have these nodes here. The reason why I'm interested, what am I trying to get at here? I maybe haven't introduced the definitions I need to explain this, I'm sorry. But, you have these nodes along the edges, right? So that means that there's some kind of twist, that some of these n numbers, this n is equal to 1 along these edges. And you can actually see that in the mirror side when you compute actually this thing. So this was maybe a little bit mysterious before. I said I take the degree -1 cohomology of the cotangent complex of X. If you actually work out what that is, it is actually non-trivial. There's something called the triple point formula for these surfaces that lets you compute that. It's basically a souped up version of the adjunction formula. And if you look at the mirror picture, you can figure out what these numbers are, and along the edge, they're actually not 0. So the point is this: the dB-sing of the boundary divisor on the mirror side is not the Fukaya category of a surface. It's one of these twisted things. Okay. All right, I'll stop there. Thank you very much.
Great, thanks so much. Let's thank the speaker for a great talk. Are there any questions?
Yeah, can I ask about the
Sure.
case, just the most basic case, the case where.
Yeah.
So.
Yeah.
I know you said you don't want to worry about, a technicality.
No, I'm happy to. Yeah, no, please.
But let me just say the one thing that slightly worries me. So of course, this Rabinowitz-Fukaya category, it's usually defined with respect to a filling.
Oh yeah.
Okay.
Yeah.
So, but in this case, there is this obvious filling.
Yeah.
Now, what I want to say is that, like in the non-exact case, it just seems we have to be very careful with what kind of structure is required in order for this category to be not so much to be well defined in the sense that like d squared equals 0, but rather like what structure does it actually depend on. So let me say what I mean here. So in this case, Z is like just this Riemann surface, right?
Yeah.
So there's another symplectic manifold, which is not the total space of the canonical, which is instead just the actual cotangent bundle as an exact symplectic manifold.
Oh yeah.
Right?
Yeah, that's totally different.
Well, it's totally different. Now take that symplectic manifold and pull back an area form on the base.
Yeah.
So now you get, this is like this kind of like magnetic cotangent bundle.
Yeah. Oh, yeah.
Okay. So I'm pretty sure that these things, that these two symplectic manifolds are like abstractly symplectomorphic.
Mm-hmm.
The total space of K of Z and this kind of magnetic.
Yeah, that makes sense. Yeah, that actually makes sense. Yeah.
But you have to be very careful about whether the invariants that you try to associate to them are invariants of the symplectic manifold, or like the symplectic manifold together with this choice of like how you measure, I don't quite say, of these actual hypersurfaces. Like what I'm trying to say.
Yeah.
Am I making sense?
Yeah.
So I know I have not thought about the higher genus case, but like in genus 1 case, there is actually some kind of issue where
Cool.
you can compute some stuff using the picture of having like a degree 0 line bundle over an elliptic curve, and you can compute some other stuff from the picture of like T star T2 with the pullback of an area form with the canonical plus a pullback, and those answers don't match up.
Wow. Okay.
Like one of them is 0 and the other one is non-zero, basically.
Yeah.
So anyway, so I just want to point out that since this is not the exact situation, there may be some extra subtleties about what we mean by this category.
No, very good. Okay. Yeah, that's a very helpful comment. Thank you.
That's all I meant to say. Okay, I have to go to a thesis defense, so unfortunately, I have to go right now. So,
Okay.
thank you.
Okay. Bye.
Other questions or comments?
I just also had want to double check my understanding.
Please.
Of PZ. So
Yeah.
is the positive end of PZ towards Z? I mean, like, is it like concave towards infinity and convex towards 0, or which way does this cobordism?
I think it's yeah, good question. Yeah, I think it's yeah, actually, yeah, it's a very good question. I think the way I've set it up, it's convex towards infinity. Yeah.
Okay.
I think so. I mean, yeah, I mean, of course, I understand what you're saying, because this looks like you're filling it by like by just the canonical bundle, like you've removed the 0 section. Yeah. I mean, the way I've set it up is that, I mean, if you have comments on, what's a better way to think about it, I'd love to hear them. But the thing is for this, the Kili-Ueda conjecture, you kind of want Z to be sitting at infinity.
Yeah, that's why I was asking. That's exactly.
You want Z to be sitting at infinity, whereas in the other one, the way it's kind of set up, it seems like Z sitting at 0. Well, yeah. Something to resolve. Yeah. Okay.
I think right in that case, you want to think about this C star bundle is being filled by U as opposed to by Z, right? As opposed to by this.
That's right. Yeah. Absolutely. Yeah. Exactly. Yeah. I mean, also, I just took the whole C star bundle. I feel like there could very well be completion issues, as you guys know, right? I mean, because you might actually need to take like some finite piece. Yeah.
I was wondering, can you say again why you expect, or why you have this Hamiltonian S1 action as corresponding to the U?
That was just sort of a degree calculation. Basically, the point is that right. I mean, I think what you have to work out is, right. I mean, one way to think about it is like there's some kind of Lagrangian correspondence from like T star S1 cross this thing to itself. I mean, so, right. And you have to figure out, with respect to the grading, what makes this correspondence gradable? Like, when is this correspondence a graded Lagrangian? And the thing is that it forces the grading on T star S1 to be not kind of the standard one, not the one where, the standard one would be kind of like, well, you think of T star S1 as C star, and then you take DZ over Z. In this one, you'd have to take like DZ. And so you get something, you get a loop that has degree 2. So that's why, so the generator has degree 2 for that reason. Just from thinking about how you have to grade things to make it compatible.
Are there any other questions?
Let's see what's happening.
Well, if not, let's thank James again. Thanks so much.
Thank you.